tanks, again, they're also composite tanks. The two nitrous and the one propane tank are all identical. They weigh only 6 pounds. And we used a paintball tank for the helium pressure end. It actually weighs 4 pounds, so the little pressure tank weighs almost as much as the full fuel and oxidizer tanks do. For thrust vector control, we took another lesson from the auto industry, or from the auto racing industry, along with some robotic servos, and we built a little platform here. As you can see, basically what we have is the mount where it hooks to the airframe, the gimbal, or the servos with a gimbal down here, and the injector is right there on the bottom. We don't have the nozzle and chamber. And then we went through some testing on this. So we tested it out this way. And then we took the whole thing, we mounted it on the vehicle, and I thought, I don't know how all of you have tested your thrust vector control systems, or even how many people have systems that require gimbling like this. But one thing that we did is, when we were looking at a way to see were we really getting the throw that we expected, and were we really getting the alignment we expected, we got laser pointer, we stuck it up the nozzle, put a little target on the ground, and drew patterns with the flight control system, just to make sure that things were behaving the way they were expected. It's a very simple test. The equipment, the laser pointer, I think cost us $14 at Office Depot. But it was very effective in terms of verifying that we had the capability we were expecting. I think most people here would really like to hear about the rocket engine. And you've seen a lot about rocket engines today. I'm going to have some video and other photos for you here shortly. But basically, the engine it's a propane nitrous engine. It's got an integral chamber throat nozzle, one solid piece of graphite that has been machined to the correct shape, and then treated with a proprietary patenting process that we have that virtually eliminates erosion. We've got an injector that's a stainless steel throttle with 2 servo control valves, similar to the servos that are used in the gimbaling system. And they independently control the fuel and oxidizer. I believe we got an off-the-shelf fuel valve, but we had to actually manufacture an oxidizer valve that gave us the behavior that we were looking for.
The fuel valve actually came off of a top fuel dragster.
Okay. And we're able to go from maximum thrust down to about 25% full throttle. And the igniter, which you'll see in a few videos here shortly, is very simple. It's actually externally inserted sparklers that are stuck up and electrically ignited in order to make sure the flame's there for when the fuel and oxidizer arrive.
Do you have interlocks on that in any way? Interlocks? Safety interlocks before starting?
At the moment we don't, no.
So as we went through engine testing, we got some really surprising. I'm going to show you a bunch of a series of videos of a number of different tests that we did. And this one goes way back when we were testing with one of the original fuel candidates with kerosene. You think we've got everything figured out exactly how it should be hooked up, but obviously the test stand was there. We were looking at could we measure thrust by how much the test stand still tilted in that case. We changed that. We decided we need to have a better test platform. So we actually built a trailer that had the fuel, the controller, and the engine mounted on the end. And started working with that. Had some successful tests. But then
Whoops.
had to play with the mixture ratio a little bit until we got it right. Once we finally did get it right, we started doing longer duration burns. We ran into another problem. shattered. And we looked at this for a while, trying to figure out what was going on, and realized that the coefficient of thermal expansion was different between the graphite and the stainless steel bolts that were holding things in place. And as the graphite expanded, it actually put pressure on that outside ring, and it shattered the graphite. So we said, well, what are we going to do about this? And Alan came up with the idea of using these Belleville washers, which basically have a spring constant, let you fasten the chamber throat nozzle assembly onto the injector.
That was actually Vanna's idea.
It was Vanna's idea? Oh,
Yeah.
okay. And what this did is let the graphite expand without damaging it as the engine heated up. But it also had an unexpected benefit, which is if you had a pressure spike, you had a burp or anything like that, or just a pressure different than what you were expecting, it would let the fuel and oxidizer sort of vent out to keep you from destroying the engine. And this actually came in useful a couple of times. We probably would have destroyed the second of the two graphite chambers that we had there had we not had this unexpected benefit. And in fact, we've now applied for a patent for that. And that's that rocket engine overpressure release system. So after all that and a number of tests, I only showed you the more exciting tests. There are many very dull tests. But then we came to this one here. Started up the engine. We were able to do a 101 second, which would be adequate for the level 1 competition. As you can see, about 45 seconds into it, we start getting a glow of the chamber. It will go from glowing red to eventually glowing white. You'll also get a demonstration here of that overpressurization release system shortly. The engine kept operating normally. It's going white hot now. Just about out of fuel. So that was, again, 101 seconds should be adequate for level